a triptych of motivations for studying simulation. But the triptych is the way that mathematicians think about simulation, the way that scientists think about simulation, and the way engineers think about simulation. And I want to use my other favorite word, compatible triptych, to emphasize that there are really no contradictions here. These 3 points of view are equally legitimate and equally compatible. Say, we thus have a compatible triptych of motivations for studying, I write, concentrated flows. When Perelman came out with his proof of the Poincare conjecture, he did not use algebraic or combinatoric methods to prove that conjecture, in which respect he had departed from the most commonly used methods for over 100 years. He instead used differential methods, conceiving the key question as involving the flow of geometry, which were described by differential equations. And he succeeded where the algebraists failed. And Terry Tao wrote an account of Perelman's proof, which also owed a great deal to the ideas of Richard Hamilton, who had conceived this idea of proving the Poincare conjecture by means of flow. Terry Tao wrote, but does not intend to publish, it's available on the archive server, a wonderful summary of Perelman's proof that includes, as footnote 3, a very excellent discussion of the relative merits of combinatoric versus flow-based computational methods. People learn algebraic and combinatorical methods for doing quantum mechanics, partly because they really work well, but partly because they're relatively easy to teach. You learn algebra before you learn differential equations. You can equally well teach quantum mechanics from a differential point of view. You can especially teach measurement theory from a differential point of view. And this point of view is sometimes called geometric quantum mechanics, largely to distinguish it from algebraic and combinatoric quantum mechanics. And the blogosphere presently is kind of lighting up with discussions of, is this new, is this valuable, is this useful? That's a long introduction to return to where we were about 5 minutes ago. Let's construct a compatible triptych of motivations for studying narrowly quantum concentrated flow, but broadly for studying quantum simulation from the viewpoint of concentrated flow, within a framework of symplectic, dynamical flow, concentrative, metric flow. If you're going to talk about dynamics, what you want to respect there is conservation laws and thermodynamics. And from a geometric point of view, dynamics is all about flow on a state space, and the only flows that respect conservation laws and respect the laws of thermodynamics are symplectic flows. In fact, a symplectic flow can be viewed as a structure that guarantees that conservation laws and thermodynamical principles will be respected. For details, you have to read our seminar notes and the supplementary material and the references in that supplementary material. But I would say, many people have contributed to this framework, but you really have to recognize, especially the early work of the Russian school by Kolmogorov and Arnold, and in the quantum domain Barrison. Then there are concentrative metric flows, and here the idea is that the only other structure you can put on a manifold that tells you how to move is a metric structure. And the first person to introduce a universal metric structure were the pioneers of quantum mechanics, Heisenberg, Schrödinger, and Dirac. It took quite a while for people to realize that the genius of these pioneers was that they not only had the metric flow that describes probability and measurement, but they also had the symplectic flow that described dynamics. And this was thus the first really successful theory of science that was able to unite symplectic and metric flows. And again, our course notes develop this point of view. it would probably be fair to say that the marriage of symplectic flow and metric flow has been uneasy. And that the full marriage probably is not going to be consummated until a successful string theory appears. Because a really successful marriage, and here I never really had the nerve to put this into the article, but it's out there on the blogosphere. A really successful marriage would be causally separable, so that I can't influence what happens in the Andromeda galaxy by what I do here. It would be relativistic. I couldn't even go to the Andromeda galaxy at the speed of light. It would not exhibit computational extravagances. There would be no way in which I can exploit the laws of nature to solve hard problems. Then finally, this theory would be unique. There would be only one theory that had those attributes of being causally separable, relativistic, and non-computationally extravagant. And right now, nobody knows how to combine those attributes, and people wrestle about this all the time, and the best theory we have for achieving this is string theory. So that is an account for the motivations of string theory as expressed from a simulationist point of view, not for publication, and frankly, I don't even have the chutzpah to put them on a PowerPoint slide. So, but with that in mind, with a certain humility in mind, induced by the fact that the symplectic flow and the metric flow don't coexist, even in the minds of mathematicians, with perfect amicability. This is way more fun than taking my aunt to the duplex ultrasound seminar here. I'm now going to write down some less visionary remarks on why large communities of mathematicians, scientists, and engineers are starting to care about this question. This already has an element of a mathematical joke in it, because there is a well-known thing called a compatible triple. If you have three structures and they have the property that any two of those structures determine the third structure, but which two is up to you, that's called a compatible triple. And ubiquitous in quantum mechanics is the compatible triple of a symplectic structure and a metric structure and a complex structure. So those are a compatible triple in quantum mechanics. If you have any two, you can determine the third. That's not an idea due to us. There's even a whole Wikipedia page on compatible triples. But if you ever wondered why I appeared in quantum mechanics, the complex number I, it's because as soon as you insist on a symplectic dynamical flow and a concentrative metric flow, these two structures together in the context of one theory require that that theory have a complex structure. So there's no real variable theory that compatibly unites symplectic dynamical flow and concentrated metric flow. Quantum mechanics is the unique theory that does that. The motivation for that earlier rambling discourse on string theory was that, gee, what if you wanted it to be, in addition to having these attributes, you wanted it to be causally separable and relativistic? Would that uniqueness still hold? And the answer is, I think a lot of people have a gut feeling that it still would be a unique theory, and it would in fact have to be whatever the successor to string theory is. So that's like the age-old dream of science. If you know what the theory of the universe has to be, there's only one theory that it could be, and everybody thinks that would be great. Abandoning that, though, here are a compatible triptych of practical motivations. There's definitely a pun there on compatible triple that I would say there's about 35 people at this university, mostly in the math department, who would go, ah, ha, 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 ha. Geometers conceive them as natural. I'm going to put underlines here because natural has a Wikipedia page on its own. It has a very definite meaning in the modern language of category theory. It means that you can express them, oftentimes in physics they say covariantly. It means that you can express them so that even two people with two very different motivations agree on what it means for symplectic and metric flow to be compatible. There's a wonderful essay by the UW's own Bob Lee in the introduction to his book on the theory of smooth manifolds, which is in our supplement. The old joke that, quote, differential geometry is the study of properties that are invariant under change of notation is funny because it is alarmingly close to the truth. So this isn't just something that geometers like. In a very real sense, a theory that doesn't have this attribute is not of any geometric interest whatsoever. So the next thing we're going to say is, what about physicists? Physicists conceive this triplet as fundamental. And here the reference is this article by Adler and Bassi that appeared in Science recently, where they ask, is quantum mechanics true, basically, I think is the title of their article. Or something. The other really great article on that is, well, it's by Berezin and Turin. Boy, and one of the best articles ever written on this subject was Schilling's PhD thesis, but I've never found out what happened to Schilling later, and I've looked really hard. And the third is that engineers embrace them as practical agents. And then the right place is the seminar notes. So this kind of begins to show you some of the federative power of these team builders. What else could bring the mathematicians, the physicists, and the engineers together, except they're never going to have the same motivations, but they are going to have a compatible triptych of motivations. So the geometers want to know the logical truth. The physicists want to know the natural truth. So the geometers submit to the discipline of rigor, and the physicists submit to the discipline of experiment. But the engineers actually have the toughest job. We want to build practical devices, and very importantly, we want those devices to be used for team building purposes. So we have to construct both the devices and the narratives. In math, the objective is proofs and algorithms. In science, theory, validated experiment. Now, I don't actually believe that one. This is just a sales tool. I think that observation is a perfectly good goal of science, too. By this, if you mean theory validated by experiment, the Genome Project was not science. It was one big observational survey. So, but you have to kind of do ugly things to the truth sometimes to get it into a small package. And pay a special attention to a guy named Kuperberg, who's a very famous quantum complexity theorist, who, however, is rather rigorously from the algebraic school. And he and I have a very polite dialogue. Well, basically, the PhD student who runs the blog says, is it worthwhile to learn this Kählerian stuff? And Kuperberg has says, well, it's not crazy, but it's probably not useful or interesting either. The third is that in engineers, the reason I'm insisting on it is this is rather a controversial point. Practical devices and well-ordered. This latter is especially important for this coming IARPA team building workshop. And I have yet to find any successful technology development effort that did not have as a necessary part of its foundation, not sufficient but necessary, the feasibility of doing an end-to-end simulation with great reliability. And that extends all the way from the building of a canal. There's no way you can build a canal from Seattle to the top of Mount Rainier. I'm sorry, that's not going to work. All that water's going to flow downhill. You cannot build a railroad from Council Bluffs, Iowa to Sacramento without carefully surveying the mountains and finding a path that does not involve grades over about 3%. You can't build a radar, you can't build a nuclear bomb, you can't build an Atlas missile, you can't fly to the moon, you can't build a VLSI chip, you can't do a genome project. Unless you have a solid basis in simulation physics to give everybody the necessary confidence that it's going to work, and to keep everybody united in a team building effort that has good morale and makes solid technical sense. So to my mind, the big advance in simulation physics is not that it's going to deliver to us truths that we didn't know, but it's going to deliver to us confidence that we didn't have. Whoa, that's great! Cut! Print that.